Hi, I'm Dr. Stacey Blersch. I'm with the Earth and Space Science Department here at Columbus State University. I teach hydrology and environmental science, but my real passion is streams and the role they play in our landscape. So I'm here at a small headwater stream in the Sagahatchee watershed near Auburn, Alabama. And I want to talk about the roles these headwater streams play, and then the process of sediment transport in stream ecosystems.
Fluvial geomorphology is the study of landforms shaped by running waters. We describe these differences in landforms by looking at the dimension of the channel, the pattern of that channel as it flows along the landscape, and the profile or the slope. We have many different watersheds of varying sizes across the United States. We're located right here in this green one in the Chattahoochee watershed, Apalachicola Basin. So the other thing when we talk about fluvial geomorphology is we have to think about fluvial processes. So the fluvial processes we are most interested in are erosion, transportation, and deposition of sediment, because that is the role of a stream, is to transport organic and mineral matter from upstream to the ocean. And this form of transport, of erosion, transportation, and deposition can be in various forms. It could be a dissolved suspended load, so it could be very small and flowing with the water. It could be bed load, which would be carried with a certain flow rate and certain stream power. And then you could also just have some of the sediment transport could just be that it's bouncing along the bottom of the stream bed, and that would be called siltation. So why do we want to look at this in terms of headwater streams? Well, headwater streams are extremely important. They're kind of like the capillaries of our lungs. They're essentially very numerous, and they provide the initial supply of water. They store and transform and transport organic matter, energy, which affect the metabolism and production. They store, transfer, and transport sediment as well as nutrients. And not only that, they can also then buffer water temperature. So headwater streams are really critical, and we're losing them at an extreme rate due to drought and development. Here you can see just the extent of headwater streams. These headwater streams are usually these first or second order streams. They're highlighted here on the left of this graph on the x-axis, and then we have on the y-axis we have how many stream miles that are opened, and then the average length of those streams. So if you look at the number of streams, 94.9% of these streams and almost 73% of the total length are in these headwaters. So while we focus on the lower portions and the parts we use more for economic development, these headwater streams are really critical, and that's why we're looking at them. So let's go back and look at then in these headwater streams, the importance, if they are supplying and transporting sediment. Let's see what that sediment actually looks like as it moves through a system. So here's a video of bed load and suspended load, and you can see as the water is flowing in this flume, you can see those different kinds. So you have some of these that are just bouncing along the bottom. That's that siltation movement. You have some that's actually considered bed load. It's moving with the flow, and then you can kind of see how it's cloudy here. You have a lighter load that's being transported with the normal flow. So sediment transport is what's happening all the time in streams, and it's something you need to look into if we're talking about long-term stability and trying to maintain connectivity to our headwater streams.
We are at the tip top of this one tributary that flows into the Sagahatchee. And this is pretty typical of most streams you'll see in the Piedmont Plateau that transition into the coastal plain. We have these sloping streams, and due to development upstream, you start to see some adjustments of those streams. Now, in geomorphology, when we talk about stability, we don't mean that it's static and stable, like a table or a bridge. We mean that it is essentially in dynamic equilibrium. Streams are living ecosystems, and they should be moved. They breathe, and they move over time. And as we know from our previous talk with Dr. Barano, they have major formations have been created from the power of these streams. It all starts here in a small headwater stream.
So one of the more critical relationships is called Lane's relationship. And this relationship essentially is this equation here at the bottom of this scale. So QS is talking about the volumetric flow, the total amount of sediment, and the size of the sediment, D50 would be the 50% average of that sediment size, is proportional then to the whole flow of discharge of the channel, the amount of water, QW, times the slope. So in other words, if you have depending on as the volume of water increases and the slope increases, you will have a larger amount of sediment and be able to have more stream power to move heavier rocks and boulders. So, and here we have, so on the left we have the sediment, and on the right we have the water. And as you start to move to, get to more steeper profiles, you would expect to have coarser sediment. And if you have more fine sediment, you expect it to be more flat. Now the problem is if you start to have some form of where things start to tip one way or the other, you could get degradation or aggradation, meaning that sediment will be dropping out, or you'll start to erode and cause erosion. And so this is what we're seeing significantly happen in our headwater streams in this transition zone between the Piedmont and into the coastal plain in the southeast.
What do I mean by dynamic equilibrium? Well, it just means that a stream is neither aggrading or degrading at a rate faster than it can keep up with its sediment transport. Streams are meant to transport sediment.
Okay. So patterns, now we're talking about more meanders and how much the stream is moving within its flood-prone width and within its valley. So this would be more looking at the sinuosity of a stream, the number of pools, the riffles, and reaches. So this would be what we talk about pattern, would be from an aerial view, what are we looking at in terms of the type of characteristics of that stream. So now let's take a look at how meanders are actually formed. How does this pattern actually exist on the landscape? And so this is a model that's based on River Geomorphology company, and we actually have one of these stream tables thanks to Dr. Denzow. And so these are videos that they've created to kind of show you how these meanders or these different conditions would exist and evolve or in the landscape as flow changes and as sediment supply changes. So this first one is just showing how a straight channel is here. So you have maybe a headwater stream, and then as water is increased up to 10 times, if you slowly start to see a meander, a regular meander starts to form, and you see these point bars, right? And erosion starting to happen. And you also notice that again, it's a living thing. While you might have the same dimension, pattern, and profile, where it's located isn't the same. It's kind of moving through the system. So it doesn't happen this quickly in a large-scale system, but this pattern does exist over time. So eventually, though, these patterns reach some form of stability, and that's what we're going to talk about next. So while the pattern and the dimensions can change, what can happen when you reach this point of stability where things start to degrade or aggrade is you start to have a deepening or a widening of the channel. So this is based on Schum et al.'s work in 1985 and pretty much hasn't changed. And it's just saying that is when you start to have these instabilities in the system, then the stream will actively erode or degrade until it reaches some new state of stability. So it starts to take sediment, deepen and widen, and then as it widens, the water slows down, it starts to drop out that sediment, and then that allows for these new banks to form when you've reached this fifth stage. And so eventually over time the channel reforms and it gets back into equilibrium. The problem is we've altered the landscape so much that many times our streams are reaching stage 3 and never really changing. They're constantly eroding, so it becomes something that we constantly have to maintain. So trying to create and get back to this stability sometimes requires us to step in and do restoration. Other times the stream has the space to change. And so this is looking at these stages, normal channel, eventually widening, aggrading, and then reforming new banks. The second half is showing you more the profile look. So what happens is usually there's a head cut and it's moving upstream until it reaches a point where it can't move anymore. And that's what we're seeing in our current streams, both in the Sagahatchee in Auburn, as well as Little Pine Knot in Buena Vista, Georgia. We are seeing this head cut due to changes in the landscape, and so sediment transport processes, this head cut moves up until it hits a point where it can't go any further. Sometimes it goes the other way. Sometimes the erosion can start where you have those dams. If you're already in the coastal plain and not near the fall line, then the head cut moves the other way. And so again, you see this movement up and down the system until it reaches equilibrium.
If you look at historically streams and you look at aerial photography, you can see these living systems moving through the landscape.
So we see this in Upatoy River in Georgia. This is downstream of our site, but this is just an aerial taken from Google, and you can see over time the erosion of each of those meander bends. You could see some abandoned oxbows that were here in the landscape, as well as some of these different ponds. And so this is typical of what would happen in a river that's allowed to move. But in urban areas, we pretty much stop the movement, and so that's why we have these really entrenched streams that have very low flows, and then during storm events are very full and have a high level of sediment transport and can move very powerful streams that end up moving really large sediment sizes.
So right now what we're going to do is we're going to kind of walk our way down and look at some things that could affect the sediment transport of a stream, and in turn then start to take a stream out of dynamic equilibrium, where the stream would have to start to adjust. So let's walk downstream now and see what else is in this landscape. As I said, this is a former farm, and I'm going to compare this as an unrestored site. It's just a preserve here in Auburn, and we're going to compare this to a restoration site that's very similar in shape and size, and see what can you do when a stream starts to get out of whack and is no longer in dynamic equilibrium. Let's go check it out. As you can see, it was a really short walk here, and we are now at a small pond. This is very typical we see in the landscape here, especially on old farms. Could have been used maybe for livestock, fishing, just a small headwater dam where they filled in with the road that we're on right now. They backfilled it and they dammed up the water here. So it's a very small pond. It's less than probably a half acre or an acre. And what we're going to look now to see is like, how could this small pond shift and change the stream downstream? Well, let's take a look. All right, well, I'm just downstream of that falls. You saw the fall line, and you could see here we're still in this first order tributary, and the stream is really actively eroding. And this is partially from that pond that's upstream and partially from the changes in the landscape. So you can see here, we're going to talk about sediment transport in the bank full width. It right now is still adjusting. You would think that that little small trickle of water, how could it possibly do this much damage? Well, that's because the sediment balance is off. And so this stream has been moving upstream, a head cut that's moved, and it finally stopped at that waterfall right there. Couldn't go any farther. So the damage is really coming from downstream and moving its way upstream because we have changed the dynamic equilibrium of the stream.
Great. So the last video we're going to show is to show this head cut moving through the system, and this is what was happening both in the tributary in the Salkehatchie as well as in Little Pine Knot. So essentially what's happening with the head cut is you're removing sediment at the lower end, and this causes one or more head cuts to start to travel upstream. So here you can see sort of this first head cut that's moving up. It's a little challenging to see, but you get incision throughout the whole stream.
So I'm here now just towards the end of this tributary, and it's been winding its way along that development I pointed out. And as you can see, I'm going to flip you around soon, you could see just how entrenched this stream has become. So here we're on the bank, and then it just drops on down. It's about 12 feet deep. You could just see the erosion that's occurred as this poor stream tries to handle all that power of water that's coming up upstream.
Okay, so that was a first order tributary and a view of the transition from the Piedmont across the fall line into the coastal plain. Let's look at the same type of features that in a different watershed. This is Little Pine Knot, which is a reach in the Upetoy Creek. So we've now moved over into Georgia, and you can see it's kind of a similar type of watershed and similar first order tributary. This is a site of a former stormwater pond, and if we zoom out, the biggest difference here is that you have a lot more rural and riparian cover than you did have in the other watershed, and yet you could have similar impacts. So let's explore a little bit more this site and how the sediment transport processes that were affecting the Salkehatchie tributary can also be evident here in Little Pine Knot. If we zoom in, we can see the reference site, which had very similar dimension, pattern, and profile of the last site that we saw at Salkehatchie Creek. And then downstream here, we're going to walk downstream and take a look at some photos and videos of what this looked like before. They actually have now removed this blockage, and so we're going to look and see what it looked like before and after. So here we have the Southeast Connectivity Assessment Project, where over 30,000 dams could be found in Georgia. This is part of a project that Dr. Sarah Gottlieb, who's involved with this research and sponsored the project in Little Pine Knot, and she has created this map to kind of show us all the potential blockages to and disconnect of our headwater streams to habitat downstream. Georgia ties with South Carolina as the worst in the Southeast, where essentially on average every 12 miles you will hit some form of dam. So these are very serious problems and things that need to be addressed. So we'll put this dam, little Lowhead Dam, inside, and you'll see how it affects the sediment transport processes. As soon as you put it in, you create a hydraulic head, and sediment starts to form over behind the dam. But you can see the bed load, the suspended bed load that's moving downstream. Eventually, though, over time, the sediment fills up behind the dam, and then more sediment will start to pass over, and you start to have deposition on the upstream side of the dam. Or I should say the downstream. And so eventually this will reach a point where you could actually have blowouts downstream of a dam, because you have this hydraulic head that builds up and comes back and creates excessive erosion. So this is usually what you're seeing up and downstream of dams. Here we are at Little Pine Knot, and this is the remnant of what the dam left behind. And here's some changes over time. The first picture, these are just from Google Maps starting in 1993. You can still see that it was a pretty significant pond, but then over time it starts to get less and less. We have pretty much every 5 years. Here in letter D is in 2007. You can see that the water is much less, and you start to see the flow is heading up. You start to see some of these areas being blown out where you see more and more water forming, and by the time you get to E, it's pretty much, you can see how this has been impacted. So this is what the reference reach looks like in this tributary. So it's really a second order, so it's a little bit bigger than what we were looking at in Sagahatchee, but you can see that these little waves have formed on the bottom of this coastal plain stream, and it's moving a lot of sediment. Over the course of a month, our instruments and various things that we've left in the stream to assess water quality and biodiversity usually get filled with sediment. So a lot of sediment is moving through the system despite having a lot of forested land in the upper watershed. But if we look at still upstream to downstream, and this is what the downstream portion looked like before it was restored, you had just excessive erosion, and we can look at the channel stability by looking at the upper banks, the lower banks, and the bottom to see how they rank. And the higher the score in this case is, the worse it is, and so the score is almost double of what it is in that upper tributary. So obviously a very unstable, actively eroding system. So in the case of this stream, and many times it would probably have to be the case also in Sagahatchee, how do you actually restore the stream back to, so you can connect it to where So in the case of this stream, and many times it would probably have to be the case also in Sagahatchee, how do you actually restore the stream back to so you can connect it to where fish could pass over natural blockages that may not have been as high as the one that we see in Sagahatchee, or in this case were man-made ones? Well, the elevation had changed so much and so significantly in this yellow and green area, it was decided that it just needed to be abandoned, and instead a new channel was built that matched the dimension pattern and profile of that reference reach upstream. So it's hoped that eventually this existing pond will eventually become a vernal pool or a wetland, and the channel will reform and reconnect downstream, and thereby avoiding this impact.
We're trying to see here with the Nature Conservancy approached us to do some baseline monitoring pre and post restoration, and also kind of take advantage of that and have an education component. So we had a course this semester on aquatic ecosystem restoration and had the students present at the Society of Ecological Restoration Conference, and then Dr. Keller has also had his foundations class out here. And our goal is to kind of make this a continued living classroom, because we want to have multiple years of data, and as we improve our methods, we'll hopefully continue to have good data and train the next round of scientists that'll be helping.